Okay, we now begin to take a look at the dynamics associated with, for example, uniform circular motion. So I've showed you this demonstration before. Recall that this is a specific type of pendulum. It's called a conical pendulum. The reason why it's called a conical pendulum is because the string here is tracing on a cone. We already went through a little bit of the kinematics of this type of motion in previous lectures. Now what we want to do is we want to apply F equals ma to this type of motion. In this particular case, there are two forces that are acting on the pendulum. There's tension from the string and the force of gravity. However, there is an acceleration associated with the pendulum. If you recall, it's inwards towards the center of the circle, and that's the centripetal acceleration. So then therefore, when we add up the forces in such a case such as this, those forces have to then equal the net force, ma. However, the acceleration is the centripetal acceleration, which is inwards towards the center of the circle. Okay, let me begin to take you through the basics of how we write F equals ma for such situations. Okay, I'm going to go ahead and move my phone. Like so. Okay, so now here's how we begin to apply F equals ma to such situations. Situations involving uniform circular motion. Uniform circular motion, by the way, is abbreviated as UCM. Now, of course, recall Newton's second law, F equals ma. And then recall what each side of the expression refers to. First of all, the left-hand side of the equation is the same thing as it always is. That is, it's the vector sum of the individual forces. In this case, however, it's the vector sum of the individual forces acting upon an object in the radial direction. That is, along the radius directed inwards towards the center of the circle. So we write the left-hand side of the expression in the following way. This symbol right here is the mathematical symbol for sum. In this case, we have the sum of the forces in the radial direction. This then equals the net force on the right-hand side of the expression, as it always does. It's just that the acceleration in this case is the centripetal acceleration, which remember is equal to the speed squared divided by the radius. So then therefore we write the right-hand side of the expression as mv squared over r. Once again, the centripetal acceleration is v squared over r. This quantity here, the net force in situations, for example, involving uniform circular motion, is given a name. It's referred to as the centripetal force. So the centripetal force is just a name that's given to ma, the net force in situations, for example, such as this. The centripetal force, however, is not an individual push or pull like tension or gravity or something like that. Instead, it is just a name that is given to the net force in such situations. It's a name given to mv squared over r. Okay, now the conical pendulum itself is actually kind of an advanced problem that I usually save for the more advanced classes. Now let me give you a basic understanding as to how the conical pendulum works. Okay, I'm going to do a little bit of erasing here. Okay, now let's specifically examine the conical pendulum. Okay, first of all, we always draw the geometry of the pendulum from the side, that is in profile, like so. So right here, for example, is the length of string L. Right here is the mass of the object, mass M. Okay, now I'm going to go ahead and construct a triangle here, like so, where this right here is the vertical direction, and we then define an angle here on the diagram as well. This is the angle made by the string with respect to the vertical direction. This angle here we'll just refer to as theta. Okay, now where is the circle about which the object is moving? Well, it's actually perpendicular to the board. So at this particular moment, as I've drawn it, the velocity vector of the object is straight out at us like this. This then means that as the pendulum circulates, the object comes out of the board over here and then goes into the board over here like so, and it then completes its circular motion on a circle that is perpendicular to the board. So the easiest way to draw that is just to draw an oblique circle like so, here on the diagram, where right here is the radius then of the circle. So at this particular moment, if I draw the object here on the left-hand side of the diagram, it has a centripetal acceleration vector, a sub c, inwards towards the center of the circle. Okay, now as I mentioned when I was demonstrating this a few minutes ago, there are two forces that are acting on the pendulum. We have first of all the weight, mg straight downwards, and then this right here is the tension T, in this direction like so, along the length of string. Okay, and then the centripetal acceleration vector is in this direction like so, inwards towards the center of the circle. So by using some trigonometry, if you add up the forces here by using F equals ma, you can then show ultimately that the acceleration vector is directed inwards towards the center of the circle. Once again, this is a more advanced topic that I treat for some of the other classes. However, understanding how the period of the motion works here, the period of the uniform circular motion, well, it's actually governed by a very simple expression that is derived by using F equals ma in such situations. Stated without the derivation itself, here is that equation for the period. Okay, the period, capital T, is equal to the following expression. 2 pi multiplied by the square root of the length of string divided by g, 9.8 meters per second squared. Once again, this expression here is derived by using F equals ma, and I do this derivation for the more advanced classes. Okay, here's how this expression works. Basically, the longer the length of string, the greater the rotational period. So I'll demonstrate this once again. Let me re-tilt my phone in order to do so. So bear with me here as I reposition my phone. Like so. Okay, and now let me begin with a length of string being rather small. If the length of string is rather small, this then means that the period is short. In other words, one rotation here happens fairly quickly, like so. Okay, let me lengthen the string, like so. When I lengthen the string, this then means that the period is longer. It takes a longer period of time, for example, for the object to circulate, like so. One aspect of the equation that I also want to mention is that the angle theta itself actually doesn't matter as long as the angle is small. So for example, I'm going to keep the length of string here the same as I'm doing right now, but now I'm going to make the angle a little bigger, like so. In this particular case, the object itself is moving at a greater speed, but the period, the time necessary for one revolution to occur, is actually exactly the same as the period here, for example, when the angle is even smaller. Once again, I'm keeping the length of string here the same as before. If we measure the period here with a stopwatch, we would find that it's exactly the same as what I did a moment ago. In this particular case, however, when the angle is smaller, notice that the object is moving at a lesser speed. Okay, now let's just take a look at a simple example associated with the conical pendulum and the use of this expression. So let me tilt the phone back. Like so. Okay, and now the particular problem that we'll examine is posted in today's folder, so go ahead and copy it down. It's just a simple plug and chug type of problem, and it's roughly what you saw a moment ago here with my demonstration. So it says that a conical pendulum has a length of 1 meter. Very simply, what is the rotational period? All that we have to do is plug into the expression here for the problem that we're given. So the length L is given to us as 1 meter. That's about what I was using in my demonstration. And then therefore from that, we can now go ahead and calculate what the period is equal to. So just plug in, nothing more than that. So 2 times pi, and then multiplied by the square root of L over G. So I have the square root then of 1 divided by 9.8. And ultimately this works out to be a period here of 2 seconds, which is pretty close to what you saw in my simple demonstration. One of the reasons why I'm spending a little bit of time here on this problem, even though we're not going through all of the F equals ma details, is because this equation right here could actually be used to very easily measure g, acceleration due to gravity, without having to bother to do a free fall experiment like we did in the earlier unit on kinematics. In order to measure g, for example, all that you have to do is take a pendulum of length L and then measure the rotational period, capital T, with a stopwatch. The only unknown at that point then is acceleration due to gravity g, which we can then solve for. In fact, you will do that process in a simple mini-lab exercise by constructing your own conical pendulum. Okay, let me go ahead and conclude this video here. I'll get to part 2 in just a few moments.